Imagine you're trying to land a spacecraft on the moon. You've got thrusters, physics, and a whole lot of ways to crash and burn. Today, we're going to explore how an AI learns to do this, not through programming every single scenario, but by learning from experience, just like we do. So here's our Lunar Lander. See how it responds to actions? The AI, we call it an agent, is constantly in this conversation with the environment. It takes an action like firing the main engine, and the environment responds with two things: a new state, where am I now, and a reward, land safely, plus cent points, crash, -100, use too much fuel, small penalty. This loop, action, state, reward, is the heartbeat of reinforcement learning. The agent's entire goal is to figure out which actions lead to the best rewards over time. Now, how does it learn? Meet Q learning. The Q stands for quality. Basically, how good is this action in this situation? Look at this simple grid world. The blue square is our agent, trying to reach the green goal while avoiding red obstacles. Traditional Q learning creates a table, like a cheat sheet, that says, when you're in this square, moving right gives you a quality score of 8. Moving left gives you 2. The agent fills out this table through trial and error. The math looks intimidating, but it's really just period. Take what you knew before, add a little bit of what you just learned. It's like updating your beliefs based on new evidence. Let's watch this in action. See that Q value table on the right? And it starts completely gray. The agent knows nothing, but as it explores, certain paths start glowing green. Those are high-quality moves. The red areas? Dead ends and bad decisions. Look at the chart at the bottom. Rewards going up over time. The agent is learning. By episode 50, it's found a reliable path to the goal. This works beautifully for simple problems. But here's where we hit a wall. That 5x5 grid, only 100 entries in our table. Totally manageable. Move to a 10x10x10 3D space. Now we need 4,000 entries. Okay, still doable. But our Lunar Lander, it doesn't live on a grid. It's got 8 continuous dimensions. Position, velocity, angle, that's infinite possible states. You literally cannot build a table big enough. So what do? We stop trying to memorize every single scenario, and instead, we teach a neural network to generalize. This is a deep Q network. Instead of a table, we've got layers of neurons. Think of them as a sophisticated pattern matching machine. Watch this. We feed in our 8 state values. They flow through these hidden layers, 128 neurons each, doing millions of calculations, and out pop 4 Q values, 1 for each action. The beautiful thing? This network can handle states it's never seen before. If it learned that falling fast at angle 30 degrees is bad, it can reasonably guess that falling fast at angle 31 degrees is also bad. It generalizes, just like you would. But how do we train it? Through gradient descent. Imagine you're lost in the mountains in fog. You want to get to the valley. You can't see far, but you can feel the slope beneath your feet. Step downhill, check the slope again, step again. That's gradient descent. The network makes a prediction. We measure how wrong it was. That's the loss. Then we nudge the weights to make it slightly better. Do this millions of times, and eventually you reach the optimal valley, the best possible Q values. Now here's the problem with regular DQN. It's overconfident. It's like a student who grades their own exam. They tend to be optimistic. See the red chart on the left? Those Q values are inflated, unrealistic. This happens because the same network is choosing the best action and evaluating how good it is. That's bias. Double DQN solves this with a clever trick. Use 2 networks. One picks the action. I think we should fire the left engine. And the other evaluates it. Actually, that's only worth 7 points, not 10. Look at the green chart. Much more accurate estimates. This simple change makes training way more stable. 2 quick but crucial tricks. First, experience replay. Instead of learning from experiences in order, we store them in a memory buffer and sample randomly. This breaks up patterns and helps the network learn general rules, not just recent events. Second, epsilon greedy exploration. Early on, the agent explores randomly. Over time, it exploits what it knows. That decay curve shows it shifting from random beginner to confident expert. So, let's recap our journey. We started with Q learning in tables. Great for simple grids. We hit the dimensionality wall with continuous spaces. We introduced neural networks to generalize. We fixed overconfidence with double DQN. We added experience replay for stability and epsilon greedy for smart exploration. Put it all together, the Lunar Lander learns to touch down smoothly every single time. This is the power of reinforcement learning. Agents that learn from experience just like we do. Thank you.